All right, so these are our notes on our rules for electron configuration and noble gas notation. We've talked a lot about how to put our electrons in atoms, but we haven't really talked about why we're going to put them there. So the first thing I've gotten questions about is why we put our electrons in these energy levels and sublevels in the order we do. And it has to do with how much energy it takes. So down here at 1s, this is going to be our lowest energy. And as we move up, we're going to get to higher and higher energy. And it doesn't always follow a sensible order necessarily. It doesn't go 1s, then 2s, then 2p, then 3s, 3p, 3d. It follows these diagonals, and it has to do with the energy, and that's as much as we need to know right now. So if we filled 1s, we follow our arrows around. We know we hit 2s, we follow our arrows around, know we hit 2p, and so on. So this is how we can do our electron configuration without drawing all our arrows. We'll do an example here in a minute. Things we need to remember when we're doing this is each sublevel, how many orbitals it has, and how many electrons each will get. And so remember our 4 sublevels, those are our letters, are S, P, D, and F. S always has 1 orbital per energy level, P has 3, D has 5, F has 7. They go up by 2 each time. And because each orbital can have 2 electrons, S can have 2 electrons, P can have 6, D can have 10, and F can have 14. The next rule we've been following but not calling it that is Hund's rule. And what this works out to be is that electrons like their space. Electrons are negatively charged, so they want to spread out as much as possible. So if they have the option to not pair, they're going to not pair. This is why when we're filling a p orbital or a p sublevel like 2p, if I only have 2 electrons, I'm going to put 1 electron in each. I'm not going to pair them because they repel. Think about this like we're getting on a school bus. If you're getting on a school bus and don't know people, you're going to sit by yourself if you have that option. Electrons are like that. And the last rule we've been following, but not calling it that, is the Pauli exclusion principle. And this says that 2 electrons with the same spin can't be in the same orbital. And the way we represent spin is by drawing our arrows. This is why every time we draw 2 electrons in the same orbital, like 1s, we have 1 up and 1 down. Because spinning electrons have magnetic fields. So think about your up arrow like the north pole of a magnet, and your down arrow like the south pole. If I tried to draw this as 2 ups, it's like having 2 north poles together. They're going to push apart. So let's practice using our Aufbau principle on arsenic. We're actually not going to draw our orbital notation. We're not going to draw the version with the arrows. We're going to show how to do it shorter. Y'all are getting pretty good at using Hund's rule and the Pauli exclusion principle, so I don't feel like I need to go back over that. So we're following the Aufbau order and then not having all our happy little blanks. This is how we're going to do our electron configuration. First of all, we need to remember that arsenic has 33 electrons because that's its atomic number. We always start at the top of this first arrow with our 1s because that's our lowest energy, and we know s has 1 orbital, so it can have 2 electrons. Then we keep going, following around. So we're going to get to 2s, which will also have 2. And then we keep going and get to 2p, which can have 6. Keep going, get to 3s, which can have 2. Let's make sure we don't lose track of our electrons. We've got 2, 4, 10, 12, so we need to keep going. Follow our arrows around. We get to 3p next, and that can have 6. Next will be 4s. We're not at 3D quite yet. Now we're going to follow our arrow around. 3D is a little higher in energy than 4s, so we can't fill that until we've already done s. And remember, 3D can have 10 electrons. And that gives us 2, 4, 10, 12, 18, 20, 30 electrons. We need 33 total, so we're going to have to keep going. And we're going to keep going to 4p. And because we only have 3 electrons left, that's 4p3. And remember, if we were drawing our orbital notation, we were drawing our arrows, it would be written out 4p, 1 electron in each, because Hund's rule says they don't want to pair unless they have to. So now the other thing we want to learn how to do is how to write these electron configurations so we don't have to write all the electrons every time. Because when you get to things like francium and you have 87 electrons, that's going to get really, really long. So for shorthand, we can use the noble gases. And remember, noble gases are group 18. And you want to use from the period from the row above because you need something with fewer electrons. What we'll learn as we learn more chemistry is that scientists don't really need to worry about the inside electrons. We need to worry about the outside electrons, which were our valence electrons. So doing the noble gas configuration means we've taken out those inside electrons. We're not worried about those. We also use noble gases because they are going to have full energy levels. We know we filled in everything at that point. There's not going to be any gaps that we'd have to worry about. Do note, you cannot use a noble gas to do its own configuration. If you're trying to do a noble gas, you've got to pick something smaller and then add more. So what you want to write down in your notes is all of these. We want to know how many electrons each noble gas has and where their configuration ends, because that will help us if we're trying to write these more quickly. So you can just look up this column on the periodic table, but it's nice to have down for reference. You don't have to think as much about it. So if we use that chart we just wrote, that's going to help us out to write our arsenic noble gas notation. And you should have the full electron configuration from just a moment ago. Remember, that was 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p3. And we know arsenic has 33 electrons. So the next smallest noble gas is going to be argon, which has 18. You can't use krypton because krypton has more electrons, and you can't take away electrons from a noble gas. So let's count up. We want to find our first 18 electrons. We've got 2, 4, 10, 12, 18. So all of this is getting replaced with my argon. Then all I have to write is what comes after that, which is going to be 4s2, 3d10, 4p3. And one of the ways we can check is we know this has 18 electrons, plus 2 electrons, plus 10 electrons, plus 3 electrons, still adds up to the 33 electrons I should have. So now you've got 2 guided practice questions in your packet. Try those on your own, and then watch the next video to see how you did.